In this session, we will be discussing a new algorithm called Dijkstra's shortest path algorithm. Okay, this algorithm is usually used to find a shortest path in a weighted graph. Okay, suppose you have weighted graph like suppose you have weighted graph. Okay, for example, if you have a graph like this. Okay, for simplicity, and these are the vertices A, B, C, D, and suppose the edges are weighted. For example, suppose these A, B, C, D can be cities, and this edges may denote the distance between them in kilometers. So 5, 7, maybe 3. Okay, so I need to find the shortest path from A to C. Okay, so that is the problem here. Okay, so Dijkstra's shortest path algorithm gives a structured way to find such paths. Okay, so we'll be discussing that Dijkstra's algorithm. It is valid both for directed and undirected graphs. Okay, so even if the edges are directed also, this algorithm will apply. Okay, so we'll be discussing this shortly. So before that, let us see some important properties of this Dijkstra's algorithm. Okay, so first of all, it is a single source shortest path algorithm. This is just for information, it is not required for you, but it's just for information. What do you mean by single source shortest path algorithm? Actually, that means so in this graph as I have drawn here, this Dijkstra's algorithm actually gives you the shortest path from A to all other vertices. Okay, that is why it is called a single source. Okay, from a single source I can find the shortest path to all other vertices. So that's why it's called a single source shortest path algorithm. Okay, and similarly it's a greedy algorithm. You know what's a greedy algorithm? At each step you are looking at the best possible choice available. You are not looking for the previous choices. You are now looking for the best possible choices available at each step. Okay, and similarly you can see the applications are abound. So if you want to find a distance as in Google Maps or some other applications like that, you can easily use Dijkstra's algorithm to use that. Okay, now let us discuss this algorithm by means of an illustration. Okay, so what is the idea of this method? Okay, so the first idea is that suppose you have a, for example, suppose you have a graph like this. For simplicity, I am just taking a undirected graph now for now. So I have vertices A, B, C, D and E here, and suppose they are weighted. Okay, for example, here this 7, 3, 4, 5, 2. Okay, suppose I need to find the shortest path from A to E. Suppose I need to find the shortest path from A to E. So I'll start with A. Okay, I'll start from A. Okay, so next what I'll do is that I'll assign weights to each of these vertices. Okay, the weights means that the total cost of arriving at those vertices. So first I'll start with vertex A and I'll assign weights to each of the vertices B, C, D and E, and this weights basically means the cost or the weight for arriving at that vertex. Okay, so if I start from A, the weight of A will be simply 0 because there is no, I am already in A, so there is no cost for reaching A itself. So the weight of A is assumed to be 0 in the first stage. Okay, it will be 0. Okay, and we have to find the weight of all the vertices. Okay, for that what I'll do is that in the initial stage I'll just allot them some temporary weights. That is simply I'll allot every vertex with a weight of infinity in the initial stage. So first step I'll assign the initial vertex with a weight of 0 and all other vertices would be assigned a weight of infinity in the first step. That's the first idea. Okay, I hope it is clear. So the weights here actually means the short cost of reaching that vertex through the shortest path. Okay, so that's the idea. Okay, so first of all I will start with vertex A. The weight of A is simply 0 because I am at A itself. Okay, and now in the first stage I'll assign a weight of infinity to all other vertices. That's the first step. Okay, now out of now you can see that all the vertices have a weight. Now out of this the shortest weight will be the vertex having the shortest weight would be taken as a permanent weight. Okay, for example, here you can see that A has a shortest weight of 0, so 0 will be taken as a permanent weight of this A itself. Okay, so you can see that in the next step onwards, sometimes some other vertex would be having a shortest weight, so that will be its shortest weight in that step. We'll come to that now. Okay, so what you have to do, first you have to assign weights to all the vertices. Out of this, the shortest or the smallest weight, the vertex having the smallest weight would be taking a permanent label. Now from now onwards the label of that vertex will not change, it will be that smallest weight. Okay, here A has the smallest weight here, so it will be the 0 will be the permanent weight of A now from now onwards. Okay, so in the next stage I will discard this A, I will only look at the next ones. That's the next idea. Okay, so once I have done with A, I have given a permanent weight to A, what I will do is that I will now go to neighbors of A. Okay, who are the neighbors of A? They are B and D. Okay, so what I will do is that we will be using a formula here. It's a very simple thing. Okay, so the weight of any vertex, so the weight, suppose you have a vertex U is there. Okay, you have the weight of U. Okay, and suppose U is reaching this V. Okay, so what the weight of this V, the weight of the new weight of V will be actually, the new weight of V will be actually the minimum of, okay, initial weight of V or weight of U plus edge UV. Okay, in other words, suppose you look at this figure. Okay, the new weight of B will be, okay, the new weight of B will be either the weight of B which is already it is infinity, or the minimum of weight of A plus edge AB. So weight of A is 0 plus edge AB is 7. So the new weight of B will be simply 7. Okay. Similarly, the new weight of D will be either infinity or the weight of A plus edge AD, that is 0 plus 2, which is 2. Okay, this is not a permanent weight, don't confuse it. This is the temporary, this is the new temporary weight which are going to give it here. So that is the idea here. Okay, so at each stage, so I'll start with an initial vertex, I'll give a weight to it and infinity to all the vertices. Out of this, the smallest weight would be assigned. So the vertex having the smallest weight would be given a permanent weight, that is the smallest weight, which is 0 here. Okay, after you're done with A, you go to the neighbors of A, that is B and D. Okay, now you can give weights to B and D by using the formula weight of V, weight of vertex V is equal to minimum of weight of V, comma the weight of U plus the edge UV. So using that idea, the weight of V will be minimum of weight of B plus weight of A plus edge AB. So once you start with A, next you are going to neighbors of A because they have edges between them. Okay, so then the weight of B will be minimum of infinity 7, which is simply 7. Okay, so using that idea, this is the just algo, this is the idea of this. So once you, so in the second stage, now we have labeled everything. Okay, so in the second stage, what are the weights now assigned to you? The weight of A is already permanent, is 0. The weight of B, we have assigned it as 7. The weight of D, I have assigned it as 2. The weight of C, I haven't assigned anything, it is simply infinity. The weight of E is simply infinity. So this is how you write the second stage. Okay, so in the second stage also, you look at the temporary labels. Already this is a permanent label, which is we are done with it, so there will be no change here. So now you are going to look at the permanent labels, temporary labels. Now out of them, choose the vertex with the smallest weight. Here the vertex D has the smallest weight, and that smallest weight will be its permanent label now. Okay, now from here onwards, the weight of D will be simply 2 only, it will not change. Okay, now we have reached the vertex D. Okay, so once you have reached D, you have to move from D, so that is only E is there, and you have to give a new weight to E. Then again you check for the smallest temporary weights, assign a permanent weight to the smallest weight there. Okay, so that is the idea. Okay, so this is how you are going to give permanent weights to each of the vertices. Okay, and this weights actually denote the cost of reaching that vertex from A. So that's the idea of this algorithm. Let us see it. Once I do some illustration, you will understand this method. Only this much you have to understand. It's a very simple thing. Okay, so this is the algorithm as I explained. So you have to find the shortest between two vertices S and T. Okay, so what is that? In the first stage, what you are doing is that initial vertex S is allotted a weight of 0 and all the vertices are given infinity. Okay, and in each step, one new vertex is given a permanent weight. As I told, at each step we are looking for the smallest weights, and the small vertex with the smallest weight will be given a permanent weight there. Okay, so that will be actually the distance of the shortest path between the source S and that vertex. Okay, so how is that going to give? How are you going to give weights to each of the new vertices? The new weights will be like this. As I told you, this is the formula there. It will be the weight of B will be actually minimum of old weight of B plus old weight of A plus edge AB. Okay, so that is the idea. Okay, so alpha ij is actually the weight of actually Vj. So that is simply minimum of old weight of Vj plus old weight of Vi, which was the previous vertex which was selected, plus the edge Wij. So that is the formula. Okay. And similarly, after that you will be taking the vertex with minimum weight and then assigning permanent weights. So that is the how we are going to do here, and an illustration is given to you here. For example, if you look at this graph, suppose I need to find the shortest path from A to C. Okay, so what I will do is that at the initial stage, what I will do is that I will give A as the weight of A as 0, both B and C will be given as infinity. The weights will be assigned as infinity. Okay, in the second stage, what I will do is that I am going to now give the weight to the next vertex of A, so the neighbor of A. So here the neighbor of A is B, so it will be simply minimum of the weight of B. The weight of B is now infinity, or the weight of A, weight of A is simply 0 plus edge AB, which is simply 4. So that is simply minimum of infinity comma 4, which is 4. Okay, so now you have given the assignment. So in the first stage the assignments were A had 0, B had infinity, C had infinity. So out of this the smallest weight is for A, so this will be the permanent weight of A and it will not change. Okay, in the second stage what you have got is that already A has the permanent weight of 0. Now the weight of B is actually 4 and weight of C is infinity. Now look at the temporary weights. The smallest weight, the vertex having the smallest weight will now get the permanent weight here. So here B has the vertex with smallest weight, not A, because already the work of A has been done and 0 is the weight is done. Now we will not touch A, we will only look at the remaining temporary vertices. That is actually B has the smallest weight here. So B will be allotted the permanent weight of 4. Okay, so in that state, the last step what you will do is, so this is the case here. The last step is that now we have reached B. So the weight of the next neighbor of B is actually C. So that will be simply minimum of weight of C, which is actually infinity. Then weight of B is actually 4 plus 5, which is simply 9. Okay, so in this stage you have got that. The third step you have got that A has weight 4, B has weight 4. Now the weight of C is simply 9. Okay, and A and B has permanent weights. So now only temporary weight left is that of C. So it will be the smallest weight of C also. So this will be this will be the permanent of C also. Okay, so from this we will see that the shortest distance from A to C has 9. So that is the idea. Okay, so this is obvious because of this graph, but this is how we are going to use in bigger graphs here. So I hope it is clear. Okay, so let us try to do an illustration here. Okay, so suppose you are being given a graph here and I need to find the shortest path from A to F. Okay, so in fact you can find the shortest path from A to any of the vertices. Okay, so that also I will discuss. So using the same method you can find the shortest path from A to any of these vertices. Okay, so suppose you have a graph like this, you need to find the shortest path from A to F. Okay, so what will I do? In the initial stage I will give a weight of 0 to A and every other vertices I will assign the weight as infinity. Okay, that is the first step. Every other vertices has now a weight of infinity. Okay, so this I will actually record it in a table here so that I can keep track in the last phase. So try to make in a table like this. So in the first stage I have allotted a weight of 0 to A and every other vertices has weight of infinity. Okay, I hope it is clear. And out of this the smallest weight is that of A, so that will be the permanent weight of A. So you can see that the smallest weight is that of A, so it will be the permanent weight of A. Again it will not change for every other step. The weight of A will be simply 0, 0, 0, etc. But these things would change. Okay, I hope it is clear. Okay, now this clear. So I have just marked the permanent weight here. It is simply 0 here. Okay, now you are at vertex way. Now we are going to look at the neighbors of it. Okay, sometimes your graph may be directed. In that case, the neighbor. So in that case, what will happen is that here the neighbors of A are actually B and C. Okay, so now we are going to look at the weights of B and C. And let me tell you, in some cases, what will happen is that if it is a direct graph, sometimes the vertex would be like this and the vertex would be like this. So in that case, we will only look at the vertex C because B is not a neighbor now, because there is no edge going from A to B. So we will not look at A to B, we will only look at A to C there. Okay, in the case of direct graph. So that will be discussed later. Okay, so in this stage now, in this case, we are now now at A. Now we will look at the neighbors of A, which are B and C. Okay, now what will be the weights of B and C now? So that will be minimum of the weight infinity, or so it will be minimum of this, or we can take weight of A. Weight of A is actually 0 plus this edge, which is 4. So what is the weight there? So it will be simply 4. And similar C also, it will be minimum of infinity, comma, or weight of A. Weight of A is actually 0 plus weight of this edge, which is actually 4. So it will be simply 4. So these two have new weights 4, comma 4. All others have infinity. Okay. So in the next step, what I will do is that I will write this as 4, this as 4, and everything else is simply infinity. I will keep track. Okay. So in this case, I am going to look at look at those vertices which are not assigned now. So we already A is assigned, so we will not look at A again. So all other vertices are actually to have temporary weights now. Okay. So out of that, we look at which vertex have the minimum temporary weight. Okay. So you can see that there are two vertices are there, B comma C. You can choose any of them. No issues there. If there is a tie coming, you can choose anyone. Suppose I am choosing B. You can also choose C. Okay, suppose I am choosing B. So that will be the permanent weight of B. So henceforth, the weight of B will not change. It will be always 4. Okay. Now you are at B. From B, you again, from the next stage, what you will do is that you will go to the neighbor of B. So the neighbor of B is again C again here. Okay. So that like that you will proceed. Okay. So you can see the next graph here. Okay. So the next graph here. So we have already assigned this one here. Okay. So now B will have weight 4, this is C has weight 4. So we are at B now. So from B, I am going to look at the weight of C. I am trying to look whether the weight of C could be again made reduced. Okay, so the new weight of C would be simply weight of C, which is 4. Okay, or so weight of, I am going to write the weight of C. It will be simply minimum of 4. So the old weight of C plus, or we can say the weight of B. So now we are coming from B to C. So weight of B. So weight of B plus edge BC, that is simply 4 plus 2, which is, so it will be simply minimum of 4 comma 6. So it will be simply 4 only. So the weight of C will still be 4. Okay. So now the table will be like this, 4 4 4. So out of, so I have filled the table like this. You can see this is table here. So already A and B has permanent weights. Now look at the rest of the edges now, rest of the weights now, that is C, D and F. Out of this, smallest is for C, so that will be now the permanent weight of C. Okay, so the smallest of the temporary weights will be the permanent weight now. Okay, so we have now given the permanent weights to A, B, C. Okay, so let me tell you one more thing. These permanent weights actually give you the length of the shortest path from A to those vertices. So if you are being asked to find the shortest path from A to all the vertices, the shortest path from A to B has length 4. The shortest path from A to C has length 4, because this is the permanent weights now. Okay, so we are actually solving the shortest path for each vertices as we are going forward. Okay, so now we are reaching C. Okay, now you can think what will happen. So once we have reached C, okay, so from C, which are the neighbors of C now? The neighbors of C are D, E and F. Now let us assign weights to them. Okay, how will you assign now? So the weight of D will be old weight of D. So minimum of old weight of D, which is actually infinity, or the weight of C. Weight of C is now 4. Okay, plus the weight of CD, which is 3. So it will be simply 7. So this will have weight 7 now. Okay, similarly, if you are looking at F, what is the weight of F? Weight of F will be minimum of infinity, or the weight of C 4 plus 6, which is simply 10. Minimum is simply 10. Okay, similarly, if you move forward for the weight of P, how will you find? It will be simply minimum of infinity, or 4 plus 1, which is simply 5. Okay, so that is 5. So now we have given weights to D, E and F. So we will update it here. So that is, so in the fourth stage you have 0, 4, 4. D has weight. What is the weight of D? D has weight 7. Okay, and E has weight 5, and F has weight 10. So E has weight 5 and F has weight 10. Okay, now look at the temporary labels here. So don't look at this ones, don't look at these ones, because already they have permanent labels. So this will not change. Okay, now out of the remaining vertices, look at the vertex having the smallest label. You can see that D is having the smallest label. So you will assign the weight of D as its permanent label. So now onwards it will not change. So this is the permanent weight of D now. Okay, so now you are reaching D. Now next step you will write from D. Okay, so once you have reached D, next step we will be writing from D. Okay, so from D there is only one vertex, that is F. Okay, so from D there is only one vertex, that is F here. Okay, so from D only one vertex is there, that is F here. Okay, so let us try to improve it again. So already, so what will be the new weight of F now? So so already we have reached, just a second, we have reached, okay, so it is wrong here, I just made a mistake. So here the smallest weight is that of E. Okay, it is of E. Okay, I am very sorry. So here the smallest weight of E is E, so this will be the smallest weight. Okay, so in that stage E will be having the permanent label. Okay, so next, now you are at E. Okay, once you are at E, now you have to look at the neighbor of E. There is only one neighbor of E, that is F. So let us try to improve the weight of F now. So what will be the weight of F now? So weight of F will be simply now already the weight of F is actually 10. So it will be either minimum of 10 or weight of E. Weight of E is actually 5 plus 3. So it will be simply 10 comma 8. Okay, so that is actually 8. So minimum of 10 comma 8. So the weight of F will now be revised to 8. So you will write it here. So weight of V, I have revised it to 8 here. Okay, so this is the right thing here. So already this is there. So now again look at the table now. So in that we have seen that already we have given permanent weights to A, B, C and D. Only D and F is remaining. Out of them, which has the smallest weight? So D has the smallest weight, that is 7. So this will be assigned the permanent label now. So only one more thing, that is F is remaining. Okay, so now D has got the permanent labeling because it's the smallest of the remaining one, so it is 7 there. Okay, so the last what you will do is that now you are at D. Okay, now you have reached D because you are given the permanent weight to D now. Okay, so once you have reached D, you will try to improve upon the weight of F. Okay, so what is this? Weight of F will be now either minimum of, already it has weight of 8, okay, or weight of D, that is 7, plus edge df, that is simply 2. So minimum of 8,9, so it is simply 8. You cannot improve further, so it is actually 8 itself. Okay, so the next step, only df is remaining. So the sixth step, only f is remaining. All other vertices have permanent weights. So 7, 5, 8. So in the last step, this will also get the permanent weight. Okay, it is 8. Okay, so that means the shortest path from A to F has a weight of 8. So okay, 8 is the shortest distance from A to F. Okay, so I hope it is clear. Okay, so what will you do in the initial stage? What I am doing, I'll give a initial vertex A as 0, and all other vertices will be given a weight of infinity, and I'll write in the table. Always try to write the table, only then you can understand it better. So out of the first row of the table, what I'll do is that I'll assign the smallest weight to that vertex as the permanent weight. Okay, here 0 is the smallest weight, so that smallest weight of 0 is assigned to A as a permanent weight. Now onwards, the weight of A will not change. Okay, now all the vertices weight change. Now I am at A now because it is the permanent weight being assigned here. Now look at the neighbors of A, they are B and C. Okay, now we are going to revise the weights of B and C. How will you revise? Using the formula minimum of old weight or the previous weight of previous vertex plus edge that between these two vertices. Okay, so here it is, weight of B will be simply minimum of infinity, comma, weight of A 0 plus 4, which is simply 4. Okay, similar C also will have weight of 4 there, and others we are not doing anything, so we'll just simply write this infinity, infinity, infinity. Okay, now we have two. Now we are going to look at the smallest weights which are not assigned now. So we can there see that B and C have smallest weight. Already you have assigned permanent weight of A, so we will not look at A, we will only look at B and C now. So you can choose either B or C. We are choosing B for time being. You can also choose C. So we will assign the permanent weight of 4 there. It will not change now. Okay, now we are to look at B. Now you look at the neighbors of B, which is again C only. You are trying to revise the weight of C, but you can see that you cannot revise it further because if you revise it, it will be simply minimum of 4,6. So I will just keep the minimum of weight of C as C, and C will be given permanent weight now. Okay, so from C again you move forward. Okay, you can see that there are 3 neighbors of C, so you can give weights to them also using the same formula. So that is minimum of old weight, comma, weight of the previous vertex plus edge of those things. So using that you can give the weights to them also. Okay, so that's the idea. So like this you will complete the table. So always remember, at each step you have to look at, you have to check at those vertex having the minimum weight. Only that will be given the permanent weight now. Okay, once you give permanent weight to that vertex, your next step should proceed from that vertex. Okay, so here because I had made a mistake here, you have to be careful there. Okay, so that's it here. It's a very simple thing. So once this is done, you can see that the minimum weight from A to F is actually 8. Okay, and similarly the minimum weight from A to D is also its permanent weight. That's actually the minimum weight from A to D is actually minimum weight distance from A to D is actually 7. The minimum distance from A to C is actually 4. The minimum weight distance from A to E is actually 5. Okay, so all this you can understand from the table. Okay, suppose you need to write the shortest path. You want to know the path. So what will you do? Okay, so for that what I will do is that it's very simple things, just like solving a Sudoku or a puzzle like that. It's a very simple thing. So we'll be writing the path in reverse order. We'll write the path in reverse order. So be careful here. So how will I write it? So what I'll do is that I'll go to the last row of the table and then I'll go backwards to write the path. Okay, I'll be writing the path in the reverse order. So we are actually need to reach the path from A to F. So I'll first go to the last table. You can see that. Look at the vertex which is being assigned permanent label in the last vertex. So last table. Okay, so which is the vertex which is being assigned permanent labeling in the last row? Which is the vertex being assigned the permanent labeling? It is F, because all the vertices have been assigned permanent labels earlier. So it is F. So first I will write F. Okay, now I am at F now. So the next step what I look is that in which row has the weight of F changed. Where was the weight of F changed in which row? Okay, so you will look backwards to the table and look at the row in which the weight of F was different from this weight. Okay, so in which row was the weight of F different? You can see that in row 4 the weight of f was different. Okay, so we'll look at row 4 and look at the vertex which had permanent weight assigned at row 4. Okay, which vertex had permanent weight assigned at row 4? You can look at this. You can say that row 4 the permanent weight assigned was actually E, because all the vertices had permanent weight assigned before. So it is actually E. So I'll write E now. Okay, so E is there. Okay, so now we have reached E. Okay, now you look at, now the weight of E is 5. Now you look backwards and look at the row in which this weight of E had changed. You can see that this weight of E had changed in the third row. Okay, in the third row the weight of E was infinity, so it was changed in the third row. Okay, so now we are at third row. Now look at the vertex which has permanent labeling in the third row. Which vertex has permanent labeling in the third row? It is actually C, so I'll write C here. So now we are at C. Okay, now look backwards for C. Look at the vertex, look at the row in which this weight was changed. You can see that in the first row this weight was different, so you have reached the first row, so that is simply infinity. So in the first row, look at which vertex had permanent weight. It was actually A. Okay, so this is the shortest path. So if I write in reverse order, I will get the shortest path, that is A, C, E, F. Okay, look at the graph. A, C, E, F. Okay, so it is from A to C, C to E, E to F. Okay, so that is how you write the shortest path. Okay, so what is the idea? Go to the last row, select the vertex which has been assigned there, write it down in your path. You are going to write the path in reverse order. Okay, and look at the next row, the previous row in which the next previous node. If there are so many, suppose there are so many changes here. Suppose there was a change of 12 here. You are not concerned with that change of 12. You look at the immediate change. Okay, you are going to look at the row in which immediate change has happened. Okay, so the weight of E is now is 8. The immediate change of E had occurred at fourth row. So we look at fourth row and look at the vertex which had permanent labeling in the fourth row. It was E. So you just write it here. Okay, similarly, once you have reached E now, you go to the immediate row above that row in which E had a weight change. So you can see that in third row E had a weight change. So in third row the permanent labeling was for C. So you write C there. Okay, and similarly for C, look at the previous immediate row before C in which C had a weight change. You can see that C had a weight change in first row. In the first row, the permanent labeling was for A. So it is actually A, C, E, F. Okay, I hope it is clear. Okay, so even you can also write the shortest path for any other vertices also. Okay, suppose you want to find the shortest path from A to, the shortest path from A to E. Okay, so you want to find the shortest path from A to E. Okay, so what you do is that you go to the row E. Okay, and you know the weight of E is F5 here. Okay, so you want to start with E. So either you can go to row in which E has permanent label. So E has permanent label in this row here. Okay, so you write E here. Go to row in which E has permanent label. It is E. Okay, now look at the row in which there was a change in that weight. Okay, so E had a weight change in this row. Okay, in that row, which vertex had a permanent labeling? It was C. So it is simply C. Okay, now we are at C now. Now look at that immediate change of C. It has happened in the first row. Okay, so you can see that in the first row the permanent labeling was for A, so it is ECA, or simply if you write ACE, this is the shortest path from A to E. Okay, suppose you have, you want another thing. Suppose you need to find the shortest path from A to D. Suppose you need to find the shortest path from A to D. So what will you do? Go to the row in which D has permanent labeling. So in which row had D had a permanent labeling? D had a permanent labeling in the fifth row. It had a permanent labeling in the fifth row. So first you write D and look at the row immediately before that in which D had a weight change. So D had a weight change in the third row. Okay, and look at the vertex in the third row which has been assigned permanent labeling. It is actually C. So write C. Okay, so once you reach C, again look for the row in which this had a immediate change. So it was actually first row. In first row it was A. So it is A, C, D is the shortest path from A to D. Okay, so likewise you can actually find the shortest path from A to any other vertices. So this is Dijkstra's algorithm. I hope it is clear. So let us do one more example. Okay, and then we'll stop. Okay, so this is very simple things, just like writing a puzzle only. Okay, so here so big examples are there. You can do it yourself if you want. So I'll just illustrate everything you can do. So always try to form a table here. So suppose you are being given a directed graph here. This is actually part of your model question paper. So try to solve it. In that they have asked you to find the shortest path from A to all the vertices. So in that case you have to draw a table and try to form find the permanent labeling for all the vertices. Okay, so let us try to do it here. So what I will do is that, so I will write a column A, B, C, D, E, F, G. G is there, no, G is not there. A, B, C, D, E, F, J, I, K. Okay, so it is not G, J, only J is there. Okay, J, I, K. Okay, so the first step I will assign weight of 0 to A, every other vertices would be assigned infinity. Every other vertices would be assigned infinity. So 0, infinity, 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 like that, everything will be assigned. Okay. In the next step, what I will do is that I look at the, so in that case you can see that this is the shortest of them, so it will be given the permanent weight of 0. Okay. In the second step, what I will do is that I look at the neighbors of A. Who are the neighbors of A? The neighbors of A are B is there, C is there, E is there, only that much, right? Okay, so what will be the revised weights now? So the weight of B will be minimum of infinity or weight of A plus 4, so it will be simply minimum of infinity or 0 plus 4, so it is simply 4. Okay, the weight of C will be again minimum of infinity or weight of A plus 5, which is actually 5. Okay, similar, the weight of E will be minimum of 8 of A, minimum of 8 of infinity, it's minimum of infinity, comma, again 0 plus 2, which is 2. Okay, so this will be simply 0, B has now weight 4, C has now weight 3, D has weight infinity, E has weight 2. Okay, F has weight infinity, 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 infinity. Okay, out of this the smallest one is that of E, so it will be given a permanent label there. Okay, similarly, now we are at E. Now we are going to look at the neighbors of E. Who are the neighbors of E? So you can see that D is not a neighbor of D, E, don't write it, E, so D is not a neighbor of E, so don't write it, so it will be here. Okay, so D is a neighbor of, D is not a neighbor of E, so it will not be right under. So here the neighbor of E is actually C is there, C is there, and also F is there. Okay, so we can revise the weights of F there. So in that case it will be like, from F it will have minimum of infinity comma weight of E. Weight of E is actually 2 plus 2, so it will be 4. So weight of F will be 4, and weight of C, can we revise it? Yes, because the weight of C is now actually 5. Okay, so it will be minimum of 5 comma weight of E, that is 2 plus 1, which is 3. So the weight of C will be now be revised to 3. So we will write here 0, 4, 3. Okay, D has infinity, E has 2, F has weight 4, others have infinity, infinity. Okay, so like that you can find the weights of everything. Okay, in this problem you can see that the weight of D will actually be infinity, because you can say there is no edge coming to D. There is no edge coming to D. All the edges are going only away from D. So you can see that in no way can we assign a weight to D. Okay, so always there is no path from A to D in this graph, because you can see that all the edges are actually coming from D only. Okay, so you can never reach D, so always you can't assign a new weight to D, so that means always the weight of D will be simply infinity. Okay, so that means that will be the permanent leveling of D. Okay, because there is, why is it infinity? Because there is no shortest path from A to D, so its weight will be unchanged, it will be infinity. So that's the only difference which happens in a weighted graphs, in a directed graphs. Okay, in some vertices may have infinite labeling. Okay, even in the final stage also, because you can't find any path from that initial vertex to that one. That's why it's infinity. So it's not wrong. That's the idea. Okay, so you can try this problem and try to find the weights of all the vertices, and also please try to do it. It's a very simple thing. Okay, and 2 more problems I have given to you. You can try doing that also. So that's Dijkstra's Dijkstra. It's not Dijkstra. It's Dijkstra's algorithm. Okay, so I hope it is clear. Okay, so that's all. Okay, thank you.